We think we know Earth. We've mapped its mountains, drilled into its crust, sent probes to its deepest oceans. We've named every continent, charted every tectonic plate, and built civilizations on the assumption that this planet, our planet, is a known quantity. But here's what almost no one talks about. The Earth you're standing on right now, it's not the first one. There was a version of Earth before Earth. It had continents. It had oceans. And life, strange, alien life, was already crawling across its surface hundreds of millions of years before anything we recognize ever existed. Tonight, we step back beyond the beginning of everything we thought we knew about our own planet. Actually, let me rephrase that. Because before Earth sounds impossible, right? How can there be an Earth before Earth? That's exactly the right question to ask. And the answer is going to surprise you in ways you're not expecting. By the end of this video, you'll understand why scientists now believe Earth has died and been reborn at least twice, and what that means for every living thing on this planet right now. We're going to walk through fire, survive a global freeze, watch life poison its own atmosphere, and witness the single most creative explosion in the history of biology. And then we're going to hold all of that up like a mirror, and look directly at the present. Let's go. The version of Earth's history we were taught in school is, to put it charitably, a highlights reel. It goes something like this. Earth forms 4.54 billion years ago from a cloud of gas and dust orbiting a young star. It cools down. Water appears. Life begins, somehow. Dinosaurs. Asteroid. Us. Roll credits. And look, that story isn't wrong. It's just aggressively incomplete. Because it skips over the parts that are most interesting. It skips the parts that make Earth's history not just scientifically fascinating but almost incomprehensibly dramatic. It skips at least 3 near-total resets of the entire planetary system. And it definitely skips the period scientists have named after the Greek word for hell, the Hadean Eon. 4.54 billion years ago to roughly 4 billion years ago. Named after Hades, the underworld in Greek mythology, not metaphorically, but because that is how the geologists who named it described what they were looking at. This was not Earth as a young, innocent planet finding its footing. This was a molten, meteor-battered, toxic nightmare of a world that bears zero resemblance to anything you've ever seen in a nature documentary. The atmosphere in the Hadean was a thick mixture of methane, ammonia, and hydrogen sulfide. No free oxygen. The kind of air that would kill you in seconds. The surface was a patchwork of hardening magma interrupted constantly, by impacting asteroids, because the solar system at this point was still full of debris left over from its own formation. There was an event called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, during which Earth was pummeled by an extraordinary concentration of asteroid and comet impacts. The surface looked less like a planet and more like a target. And the moon, this detail always gets me, the moon was only about 22,000 kilometers away. Today it sits nearly 384,000 kilometers out. Back then, it was close enough that the tidal forces it exerted on Earth were pulling ocean-scale waves of liquid rock across the surface. Tides hundreds of meters high. On magma. Here is where the story gets scientifically awkward, though. Because almost none of this is directly observed. It's inferred. And the reason it's inferred rather than read directly from the rock record is that we have almost no intact rocks from the Hadean Eon. The oldest known intact rock formation on Earth is the Acasta gneiss in Canada's Northwest Territories, 4.03 billion years old, and even that has been so thoroughly metamorphosed, so subjected to heat and pressure over billions of years, that it's like reading a document that's been photocopied 17 times and then left in the rain. The information is there, but you have to work very hard to extract it. I had a geology professor once tell me that studying Earth's early history is like being a detective at a crime scene where someone vacuumed up almost all the evidence. You're working with crumbs. Beautiful, billion-year-old crumbs, but crumbs. The crumbs, though, are extraordinary. Because the most important evidence we have from this period isn't rock at all. It's crystals. Specifically, zircon crystals, tiny, harder than almost anything grains of zirconium silicate found in the Jack Hills region of Western Australia. And those crystals are changing everything. Zircon is remarkable because it is, in geological terms, indestructible. While the rocks around it get melted, crushed, and chemically transformed by billions of years of geological activity, zircon just sits there. Intact. Holding its secrets. The Jack Hills zircons are dated to 4.4 billion years ago, making them the oldest known material on Earth. But their age is almost secondary to what they contain. When zircon forms in the presence of liquid water, it incorporates oxygen atoms in a specific ratio, specifically, the ratio of oxygen 18 to oxygen 16 isotopes, expressed as the delta 18O value. The Jack Hills zircons have delta 18O values that are anomalously high. And that anomaly means only one thing: these crystals formed in an environment with liquid water. Liquid water. At 4.4 billion years ago. In what we had assumed was the middle of Hadean Hell. A landmark study by John Valley and colleagues, first published in 2001 and confirmed with higher precision techniques in 2014 using atom probe tomography at the University of Wisconsin, established this finding firmly enough that it now anchors what geologists call the cool early Earth hypothesis. The idea is not that the Hadean was comfortable, it absolutely was not. But that even within the chaos of constant bombardment and volcanic outgassing, there may have been stable pockets. Regions where the surface had cooled enough, where liquid water could collect and persist. Not a global ocean, perhaps. More like oases. Think about it this way: even in the middle of a volcanic eruption, there are pockets of cooler ground where things survive. Earth might have worked the same principle, just scaled up to planetary proportions. The implication of this is staggering. Because if liquid water existed at 4.4 billion years ago, and the chemical window for life to originate potentially opened 300 to 500 million years earlier than mainstream science had admitted, then the timeline of life on Earth shifts dramatically. That's not a small shift. 300 million years is the span between when the first amphibians crawled onto land and right now. That's an enormous amount of time during which life could have been doing things we never suspected. There's something deeply poetic about this. These researchers, holding a crystal smaller than a grain of sand, realizing they're holding something that formed before any stable ocean, before any continent, before Earth itself was truly what we'd recognize as Earth. And locked inside that tiny grain, a record of water. Of the potential for life. Preserved perfectly for 4 billion years in the middle of one of the driest landscapes on the planet. The scientific community's reaction to the cool early Earth hypothesis was not uniformly enthusiastic, it's worth saying. Some researchers argue that the high delta 18O values can be explained by processes that don't require liquid water at the surface. This is a live debate. The 2014 atom probe confirmation strengthened the water hypothesis considerably, but the word confirmed in early Earth science almost always comes with asterisks. What we can say is this: the evidence suggests water, the evidence is solid, and the alternative explanations are less parsimonious. That's about as strong a statement as you get in this field. But here's what the zircon evidence actually does, regardless of which side of the debate you find more convincing. And it asks a question that the textbooks definitely do not ask. If the conditions for life existed this early, is there any chance life actually appeared this early? The oldest confirmed biosignatures on Earth are about 3.7 to 3.8 billion years old. But there is one set of findings, still contested, still being argued about in journals, that pushes that number to 4.28 billion years. Which would mean life on Earth appeared almost immediately after the planet formed. Almost as if it was waiting for the door to open. In 2017, a team led by Matthew Dodd at University College London published a paper in Nature describing microscopic structures found in the Neuvwoodgitic Belt in Quebec, Canada. The Neuvwoodgitic Formation has a disputed age. Estimates range from 3.77 billion years to as old as 4.28 billion years, depending on which dating method you use and which researcher you ask. Dodd's team found tiny tubes and filaments made of hematite, an iron oxide mineral, arranged in structures that are strikingly, almost uncomfortably, similar to the fossilized remains of iron-oxidizing bacteria found today near hydrothermal vents. If these structures are biological in origin, and if the older age estimate is correct, then life on Earth began within the first 200 million years of the planet's existence. That would be extraordinary. Critics of the Neuvwoodgitic findings argue, fairly, that hematite can form similar structures through purely geological processes, and that the age dating is too uncertain to draw strong conclusions. The finding remains officially possible in scientific terms, which in science speak means we can't rule it out and some of us think it's real. More firmly accepted is evidence from Greenland. The Isua Greenstone Belt, dated with confidence to about 3.7 billion years ago, contains what Alan Netman of the University of Wollongong identified in 2016 as stromatolites, layered dome and cone structures produced by microbial mats growing in shallow water. Stromatolites are significant because, unlike the hematite tubes at Neuvwoodgitic, they cannot be convincingly explained by non-biological processes. They are a smoking gun. Faint, ancient, deeply buried, but a smoking gun nonetheless. So what kind of life was this? It was nothing you would recognize. No plants. No animals. Not even cells with a nucleus. These were archaea and bacteria, the simplest, most ancient forms of life we know. And they were not delicate. They were built for hell. The organisms that dominated early Earth were extremophiles, creatures adapted to conditions that would kill anything currently walking on land. Some thrived at temperatures between 60 and 120 degrees Celsius. Some metabolized sulfur compounds or iron instead of oxygen. Some lived in water with acidity levels similar to stomach acid. The most remarkable metabolic pathway among them was chemosynthesis, extracting energy from chemical reactions between minerals and water, completely independent of sunlight. These organisms didn't need the sun. They didn't need a stable surface. They needed a vent, and heat, and chemistry. That's it. The Lost City hydrothermal field, discovered in the year 2000 in the Atlantic Ocean, is the best living analog we have for early Earth's deep environments. It's a field of carbonate chimneys, some nearly 60 meters tall, where alkaline fluids mixing with seawater create exactly the kind of chemistry that many origin of life researchers think produced the first metabolic reactions. Life at Lost City today includes methane-producing archaea living inside the chimney walls. They have no idea that sunlight exists. They've never needed to know. There's a weird comfort in all this, honestly. When I first learned about Hadean Earth, the constant bombardment, the toxic atmosphere, the boiling oceans, it felt like the most hostile place imaginable. And yet something figured out how to live there. Life is stubborn. Impossibly, beautifully stubborn. For nearly 2 billion years after those first microbes appeared, that was the entire story of life on Earth. A world of invisible, ancient, unkillable things doing chemistry in the dark. No predators. No movement you could see. Just metabolism, replication, and time. Birth version 1.0. Microscopic. Relentless. And completely unaware that one lineage among them was about to commit the planet's first act of ecological catastrophe. Here is something that sounds like a paradox until you sit with it. The most destructive event in the history of early life on Earth was caused not by an asteroid, not by a supervolcano, not by any external force at all. It was caused by photosynthesis. Specifically, by tiny, single-celled organisms called cyanobacteria, which evolved the ability to split water molecules using sunlight and release oxygen as a byproduct. From their perspective, oxygen was garbage. A metabolic waste product with no value whatsoever. They were just doing what life does, extracting energy from their environment as efficiently as possible. They had no idea they were loading a gun pointed at almost every other living thing on the planet. Before the cyanobacteria got going, Earth's atmosphere contained essentially no free oxygen. The dominant gases were nitrogen, carbon dioxide, methane, and traces of other compounds. And the organisms that had been happily evolving for over 1 billion years were built for exactly this chemistry. Oxygen, to them, was not a breath of fresh air. It was a toxin. A reactive, destructive molecule that attacked the very proteins and DNA their cells were built from. For a while, a long while, the oxygen problem was contained. As cyanobacteria began pumping oxygen into the ocean, that oxygen immediately reacted with dissolved iron in the water, oxidizing it and causing it to precipitate out as iron oxide, rust, which sank to the seafloor in thin layers. We can see those layers today. They're called banded iron formations, and they're exactly what they sound like, striped sequences of iron-rich and silica-rich rock, alternating in bands. They're found on every continent. They represent the chemical record of oxygen trying to enter the world and being repeatedly neutralized by the iron buffer in the ocean. And here is the extraordinary detail: about 65% of all the iron ore we mine today, the iron that goes into our steel and our infrastructure, is banded iron formation. Every bridge, every skyscraper, every car frame, somewhere in its origin is the death spiral of an ancient ocean, soaking up the oxygen exhaled by organisms that lived 3 billion years ago. But the buffer couldn't last forever. Eventually, around 2.4 billion years ago, the dissolved iron in the ocean was exhausted. And once the iron buffer failed, oxygen had nowhere to go but up. Into the atmosphere. The great oxidation event had arrived. What followed was, by any reasonable definition, an apocalypse. Methane, which had been a major greenhouse gas in Earth's atmosphere, helping keep the planet warm, reacts with oxygen to produce carbon dioxide and water. As oxygen levels rose from trace amounts to perhaps 1 to 3% of the atmosphere, methane was systematically destroyed. The greenhouse effect that methane provided collapsed. Earth's temperature plunged. And the planet entered its first major glaciation, the Hadean Eon, which lasted from roughly 2.4 to 2.1 billion years ago, and may have been severe enough to qualify as the first snowball Earth event. By best estimates, close to 90% of all anaerobic life, life that had been the only life on Earth for over 1 billion years, went extinct. Not in a sudden flash, but over hundreds of millions of years, as oxygen slowly saturated environments that had been safe for so long. This is the first mass extinction in Earth's history. And it was caused not by an external catastrophe but by one of life's own innovations. I find myself thinking about this a lot. We tend to frame extinction as failure, as something imposed on life from outside, a punishment for existing in the wrong place at the wrong time. But the Great Oxidation Event shows something different. Sometimes the most transformative thing in a world's history is the thing its own inhabitants created, without understanding what they were creating. The creatures that died in the oxygen apocalypse didn't die for nothing. Their death cleared the way for something incomparably more complex and capable. Aerobic respiration, using oxygen, is roughly 15 times more energy efficient than its anaerobic equivalent. Once oxygen was available, life had access to an energy source that made everything that came next possible. Every mitochondrion in every cell of your body is a direct descendant of that transformation. For nearly 1 billion years after the Great Oxidation Event, a span geologists call, with great affection, the boring billion, Earth maintained a kind of dynamic stasis. Oxygen levels plateaued. Life remained microbial, though more diverse than before. The planet was rearranging itself tectonically, building and breaking supercontinents, but the biological story was relatively quiet. The boring billion ends around 750 million years ago. And it ends with something that makes the Great Oxidation Event look mild. It ends with Earth trying to kill everything at once. The Cryogenian period runs from approximately 720 to 635 million years ago. And within it are two of the most extreme climate events in Earth's history, events that, if the evidence is read correctly, resulted in the complete freezing of this planet from pole to equator. Not very cold. Not ice age. Completely frozen. Every ocean surface locked under kilometers of ice. Every continent buried. Pole to equator, wall to wall. Geologists call it Snowball Earth, and the evidence for it is one of the more elegant pieces of detective work in earth science. Diamictites, a type of glacially deposited sedimentary rock, chaotic and unsorted, dropped there by moving ice, have been found on every major continent from the Cryogenian period. That alone could be explained by continental drift, continents having been near the poles at the time. But here is where paleomagnetic evidence becomes decisive. These rocks carry a magnetic signature that records where Earth's magnetic poles were when the rocks formed. And the signature shows that many of these glacial deposits formed at what were then equatorial latitudes. Ice at the equator. Complete coverage. The trigger was likely the breakup of the supercontinent Rodinia, which began around 750 million years ago. As continents drifted into tropical regions, increased weathering, the chemical erosion of rock, pulled carbon dioxide out of the atmosphere faster than volcanoes could replace it. The greenhouse effect weakened. The planet cooled. And once ice started forming, it created a feedback loop that accelerated its own spread. Ice reflects sunlight far more efficiently than open ocean does, the albedo effect, so as ice coverage grew, more sunlight bounced back into space, the planet cooled further, more ice formed, and so on, until you cross a tipping point somewhere around 30% ice coverage, beyond which total planetary glaciation becomes essentially unavoidable. The Sturtian glaciation lasted from approximately 717 to 660 million years ago. 57 million years. I want to let that number land properly for a moment. 57 million years ago from today, the dinosaurs had just gone extinct. We are talking about a stretch of frozen silence equal to the entire span of the age of mammals. And during the entire Sturtian, Earth was a white ball. No liquid ocean surface. No seasons in any meaningful sense. A planet that looked, from space, like a billiard ball wrapped in a freezer. After a geologically brief warm interval, the Marinoan glaciation hit, approximately 650 to 635 million years ago, lasting about 15 million years. Earth froze completely twice in quick succession. Life refused to comply with the obvious conclusion. The survival mechanism is still debated, but the best current hypothesis involves what researchers call refugia, pockets of survivable environment maintained by geological heat. Hydrothermal vents under the ice. Thin ice regions near volcanic islands where sunlight could still penetrate. The analogy used most often today is Lake Vostok in Antarctica, a liquid lake buried under nearly 4 kilometers of ice, completely isolated from the surface, and yet containing microbial life. That's not a perfect analog for snowball Earth, but it captures the principle: ice is an insulator as much as it is a barrier. If the heat source is below, life finds the gap. The thaw, when it came, was neither gentle nor gradual. While the ice persisted, volcanoes continued erupting, as they always do, pumping carbon dioxide into the atmosphere. With the ocean locked under ice, there was no weathering to remove that CO2. Over millions of years, it accumulated, until the greenhouse effect became powerful enough to crack the ice. And when it cracked fast. Geological models suggest the final deglaciation could have happened in as little as a few thousand years, releasing enormous volumes of meltwater into a chemically starved ocean in an almost instantaneous, by geological standards, flood of nutrients. Phosphorus, iron, nitrogen compounds. Everything that had been locked up under ice, accumulated from volcanic and geological sources, suddenly available all at once in an ocean full of life that had survived by the narrowest possible margin. You couldn't design a more effective pressure cooker for biological innovation if you tried. What came out of it, roughly 635 million years ago and into the Ediacaran period, was the first evidence of truly complex, multicellular life. And what came after the Ediacaran, what the snowball's legacy ultimately built toward, remains the most breathtaking event in the history of biology. The Cambrian explosion. 538 to roughly 518 million years ago. 20 million years during which the biological world went from simple, soft-bodied, largely sessile organisms to an explosion of body plans so varied, so creative, so structurally inventive that it strains credulity even knowing it happened. Before the Cambrian, the Ediacaran period shows us life's dress rehearsal. Creatures like Dickinsonia, flat, oval, ribbed organisms that could grow up to a meter long, with no identifiable mouth, gut, or sensory organs. Charnia, which looked like a fern frond and grew anchored to the seafloor, filtering nutrients from the water. These were alive, certainly. They were multicellular, certainly. But they were alien in the most fundamental sense, operating by biological rules that no longer apply to anything living today. They weren't outcompeted exactly, they were simply left behind by what came next. What came next was something for which Darwin himself, in On the Origin of Species, confessed he had no satisfactory explanation. The apparent near-simultaneous appearance of almost every major animal body plan in the fossil record within a geologically tiny window. He called it, with characteristic bluntness, the gravest objection which can be urged against my theory. We now understand that the Cambrian explosion was not quite as instantaneous as the fossil record makes it appear. The Ediacaran transition was longer and more gradual than early interpretation suggested. But even accounting for that, the rate of morphological innovation during the Cambrian is without parallel in all of Earth's history. Roughly 0.4% of Earth's existence accounts for the body plans of about 95% of all animals that have ever lived. The Burgess Shale in British Columbia, discovered by Charles Walcott in 1909, preserves a snapshot of Cambrian life so detailed, with soft tissues, eyes, internal organs visible as impressions, that it reads like a catalogue of alien life. Anomalocaris, The apex predator of its time, up to a meter long, with compound eyes containing an estimated 30,000 lenses each, and grasping appendages that folded prey toward a circular, tooth-lined mouth. Hallucigenia, a creature so bizarre that when it was first reconstructed, scientists put it upside down and identified the head on what turned out to be the tail. Opabinia, 5 eyes mounted on stalks and a frontal nozzle-like proboscis, with no identifiable living relatives. Wiwaxia, covered in overlapping scales and defensive spines, its evolutionary affinities debated for decades. Some of these animals are so unlike anything alive today that when paleontologists first described them, they created entirely new animal phyla to contain them, only to later realize, with more specimens and better analysis, that they were strange early relatives of groups that still exist. The creativity of that moment in life's history is hard to overstate. Evolution was, in a sense, trying everything at once. Filling an ocean that had been cleared and nutrient-loaded by 2 snowball catastrophes with every morphological experiment it could generate. What triggered this? The honest answer involves several simultaneous forces, which is both scientifically accurate and slightly unsatisfying. Atmospheric oxygen had risen to perhaps 10% or more by the early Cambrian, high enough to power the kind of active, muscular, energy-intensive bodies that the explosion required. The nutrient flood from post-snowball meltwater had primed the ocean's chemistry. New genetic regulatory tools, Hox genes, which act as master switches controlling body segment development, had emerged, allowing modular construction of complex body plans from a relatively small set of genetic instructions. And crucially, once the first predator evolved, an evolutionary arms race began that drove diversification exponentially. Eyes appeared. Then armor. Then speed. Then claws. Each innovation forced counter-innovations in everything else. The Cambrian was a biological war that produced a biosphere. Among the creatures in the Burgess Shale is one that I keep coming back to. Pichia gracilens. Small, leaf-shaped, maybe 5 centimeters long, swimming with lateral undulations through the Cambrian Sea. Unremarkable in appearance. But Pichia had a notochord, a stiff, rod-like structure running along its back, the precursor to a vertebral column. Pichia is the earliest known chordate. The beginning of the lineage that would become fish, then amphibians, then reptiles, then mammals, then us. There is an unbroken chain of life connecting you to that 1-centimeter creature in a Cambrian sea 520 million years ago. Every eye that has ever seen a sunset. Every hand that has ever held another person's. Every mind that has ever looked up at the stars and felt something it couldn't name. All of it traces back to Pichia. We are Earth's latest version of a very, very old idea. I've read about the Cambrian explosion probably 50 times at this point. And every single time I get to Pichia, this tiny, unremarkable thing, I feel something I can't fully articulate. Humility, maybe. Connection. That little creature is us. It had no idea what it was starting. Birth after the Cambrian was a more recognizable world. Complex animals. Ecological hierarchies. Predator and prey. But the story didn't become peaceful. From the end of the Cambrian to today, Earth has undergone 5 mass extinctions, events that eliminated somewhere between 75 and 96% of all species alive at the time. 5 apocalypses. And the pattern they reveal, when you lay them out together, is one of the most important things Earth's history has to teach us. The Endordovichian extinction, 443 million years ago, claimed roughly 86% of all species, caused primarily by a massive glaciation as the supercontinent Gondwana drifted over the South Pole, combined with the sea level drop that exposed and drained the shallow seas where most marine life lived. The late Devonian extinction, spanning roughly 375 to 360 million years ago, unfolded slowly over perhaps 25 million years, eliminating about 75% of species through a combination of events including ocean anoxia, widespread oxygen depletion in the deep ocean that created enormous dead zones. The end Permian extinction, 252 million years ago, is in a category of its own. The Great Dying. It is not clear how close Earth came to losing all complex life. What is clear is that approximately 96% of marine species and 70% of terrestrial vertebrates were gone by the end of it. The Siberian Traps, a region of Siberia where colossal volcanic eruptions pumped magma and gases into the atmosphere for roughly 1 million years, are the primary driver. Ocean temperatures rose by an estimated 10 to 15 degrees Celsius. Ocean chemistry became acidic enough to dissolve the carbonate shells of marine organisms. Atmospheric CO2 likely reached somewhere between 4,000 and 8,000 parts per million, compared to today's 420. Recovery took between 10 and 30 million years. The end Triassic extinction, 201 million years ago, cleared approximately 76% of species and opened the ecological space that allowed dinosaurs to diversify and dominate. The end Cretaceous extinction, 66 million years ago, took the dinosaurs themselves, along with 3/4 of all species, in the aftermath of the Chicxulub asteroid impact, combined, it's now believed, with extensive volcanism from the Deccan Traps in what is now India. 5 extinctions. Each one reshaping the biological landscape so completely that the world before and the world after are barely recognizable as the same planet. And through all of them, a consistent pattern: organisms adapted to stable, specialized conditions collapse. Generalists, burrowers, organisms with rapid reproduction cycles, deep water species, these tend to survive. And in the aftermath of each extinction, the survivors diversify into the vacated ecological niches with astonishing speed. Every mass extinction is simultaneously a catastrophe and a Cambrian explosion in slow motion. I want to be careful about where I go with this next part. This documentary isn't built on despair, and I'm not interested in finger-pointing. But intellectual honesty requires acknowledging what the geological record is currently showing. Current biodiversity loss rates are estimated by researchers including E.O. Wilson and documented in IPBES assessments at roughly 100 to 1,000 times the background extinction rate, the natural rate at which species typically disappear over geological time. The Holocene extinction, increasingly called the Anthropocene extinction, is being documented in real time. And the mechanism is, for the first time in 4.5 billion years, a single species operating as the driver. The geological record does not care about our intentions. It simply records what happened. Right now, it is recording what happens when one species acts at geological scale. But here is where the geological mirror becomes genuinely useful, not as an instrument of guilt, but as a source of honest perspective on what resilience actually looks like. The CO2 comparison is instructive. The Siberian Traps at their peak were releasing an estimated 3 to 4 billion tons of CO2 per year over roughly 1 million years. According to IPCC data from 2023, human activity currently releases approximately 37 billion tons per year. That rate is roughly 10 times the Siberian Traps peak, and the Siberian Traps caused the Great Dying. This is not alarmism. This is reading the geological record directly and comparing units. At the same time, and this matters enormously, the geological record also shows something else. Life survived the Hadean. It survived the Great Oxidation Event. It came through 2 complete planetary freezes. It endured 5 mass extinctions, each of which would seem, from the inside, like total annihilation. The 3.5 billion year track record of life on Earth is an unbroken chain. Life has never, not once, gone completely extinct. That is a remarkable thing to say about any system in any context. The question the geological record asks, honestly, is not, will life survive? Life almost certainly will. Extremophiles, those ancient, indestructible metabolic machines that figured out how to live in Hadean hell, are still here. Tardigrades, those extraordinary eight-legged microscopic animals sometimes called water bears, survive vacuum conditions, radiation doses 1,000 times lethal to humans, temperatures ranging from close to absolute zero to 150 degrees Celsius. Evolution solved the problem of surviving extreme Earth 3.5 billion years ago. The solution is still operational. The real question is, which life? And where in that inventory do we fall? Your blood, by the way, has a salt concentration that approximates the composition of the Cambrian Ocean. Human embryonic development passes through stages where structures resembling gill slits form and then reorganize into jaw and ear components, a physical replay of evolutionary transitions that happened in Devonian seas. Your mitochondria, the energy-producing structures in every one of your cells, are descended from ancient bacteria that were engulfed and incorporated by early eukaryotic cells roughly 2 billion years ago. You are not just living on an ancient planet. You are built from its memory. Your body is a museum of every major transition in Earth's history, compressed into 100 trillion cells. Everything we've discussed tonight is still here. The Hadean heat, trapped in Earth's interior and still driving plate tectonics. The Great Oxidation Event's legacy, layered in iron ore deposits on every continent. The Cambrian creatures, fossilized in the pages of the Burgess Shale. The Great Dying, recorded in the chemical signature of the Permian-Triassic boundary wherever it's exposed. Earth is not a planet with a history. Earth is its history, still unfolding, still encoding the present into the rock that will baffle and delight whatever species studies it 300 million years from now. The Grand Canyon is the most famous cross-section of this archive, 2 billion years of Earth's diary visible in exposed cliff faces, each color band a different chapter, from the Vishnu basement rocks at the bottom to the Kaibab limestone at the rim. Pick up any piece of limestone and you are holding compressed bodies of marine organisms. Coal is carboniferous forest, compressed and chemically transformed. Iron ore is the chemical residue of the Great Oxidation Event's mass death. We quarry our geological heritage and build cities from it without, usually, knowing what we're holding. Carl Sagan's pale blue dot photograph, Earth captured from 6 billion kilometers away by Voyager 1 in 1990, shows our planet as a fraction of a pixel in a ray of scattered sunlight. From that distance, you cannot distinguish the Cambrian seas from the frozen snowball, cannot see the evidence of the Great Dying, cannot locate the boundary between the world before and after the Chicxulub impact. It's all compressed into one small, improbable point of light. And yet it's all there. Every version of Earth. Every catastrophe and every recovery. Every ancestor. Every extinction that cleared the way for something new. In 4.5 billion years, through everything we've walked through tonight, Earth has never stopped being Earth. It has been remade, restarted, nearly silenced. But it continued. And so did life. So what does all of this, the Hadean water evidence, the Cambrian explosion, the 5 apocalypses, the snowball recoveries, actually tell us about what comes next? In about 250 million years, the continents currently spread across Earth's surface will converge again into a new supercontinent. Several competing models exist. The most cited projection, sometimes called Pangea Ultima, closes the Atlantic as the Americas push back toward Europe and Africa. The Mediterranean will disappear entirely as Africa continues its northward movement into Eurasia, building mountain ranges comparable to the Himalayas along what is now southern Europe. The interior of whatever forms will be extraordinarily hot and dry, Triassic conditions, by the best analogy in the geological record. Life will look nothing like it does today. Further out, somewhere in the range of 500 to 800 million years from now, the sun's slowly increasing luminosity will create a more fundamental problem. The sun brightens by roughly 10% per billion years, steadily and inevitably. At some point in that half-billion to billion-year window, the average surface temperature of Earth will exceed the threshold for stable liquid water. Before that terminal threshold is reached, a feedback loop involving silicate weathering will draw atmospheric CO2 below the minimum required for photosynthesis. Plants will fail. The food chains built on photosynthesis will collapse. Surface life, as we know it, will end, not explosively, but in a long, gradual warming. Not with a bang. What persists after the surface fails? Probably exactly what persisted through snowball Earth. Chemosynthetic organisms in the deep ocean, feeding on heat and chemistry. Extremophiles in hydrothermal systems. The deep biosphere, microbes that live in rock pores kilometers underground, surviving on trace energy, reproducing over geological timescales. Life going back underground, back to the conditions that produced it in the first place. Earth version 1.0 was a world of underground and submarine life. It's possible, even likely, that something analogous to Earth version 1.0 will be Earth's final chapter, billions of years hence. For now, though, the more pressing question is what role this current version of life, our version, plays in the transition to whatever version comes next. Three scenarios emerge from the pattern the geological record shows us. In the first, current trajectories produce a mass extinction on the scale of the Great Dying. The geological record shows recovery follows, 10 to 30 million years for biodiversity to rebuild. Life continues. We do not. In the second, the species currently acting as the geological force becomes capable of managing that force, intentionally shaping atmospheric chemistry, deliberately preserving biodiversity, engineering habitats in ways that slow or redirect the current trajectory. Earth version, human. Something genuinely unprecedented in geological history. In the third, this species extends itself beyond Earth, to other planets, other systems, and Earth, for the first time in 3.5 billion years, becomes a planet without its dominant intelligence. And it recovers. Forests return to the places we've cleared. Oceans rebuild their chemistry. Something new fills the niches we leave behind. None of these is Earth's extinction. All of them are the next version. I'll admit, I started this project wanting to find something definitive. A clear answer about what all this deep history means for right now. What I found instead was more questions. Better questions. Richer questions. I think that's what serious engagement with Earth's history does. It doesn't close the story. It shows you how long the story actually is. We started tonight with a question that sounds like a paradox: was there a version of Earth before Earth? And the answer, it turns out, is yes, several. A Hadean Earth that no one who hadn't studied it could possibly recognize as our planet. An early ocean world where the first microscopic life found ways to metabolize in conditions we'd call impossible. A world that poisoned itself with oxygen and nearly froze solid not once but twice. An ocean that, in a geological instant, filled with every imaginable body plan. A planet that has survived 5 apocalypses and is currently cataloging the early evidence of a 6th. Earth is not a stage on which life's story plays out. Earth is the story. It is a process, 4.5 billion years of continuous reinvention, discarding old versions of itself to build new ones, using catastrophe as raw material for innovation. Every single time, without exception across the entire span of the geological record, life found a way. The version of Earth you live on right now is not the first. It will not be the last. We are one chapter in a story that started in fire, that has outlasted everything thrown at it, and that has no visible ending. And I find that more studying than frightening. Because it means the story is not over. The most interesting chapters may not yet have been written. If you want to follow what comes next, because the next question this research led me to is whether any of the 400 billion star systems in the Milky Way might contain a planet currently going through its own Cambrian explosion, and what James Webb is quietly beginning to show us about the atmospheric chemistry of distant worlds, then stay with us. We're going to try to find out together, and the answer to at least one of those questions is stranger than the question itself. And if the idea that your planet has already died and been reborn multiple times, that the ground under you carries 4.5 billion years of memory in its rock, that every catastrophe in this story produced something stranger and more resilient than what came before it, if that idea stays with you past the end of this video, then we did something worthwhile tonight. Go outside, if you can. Look down at the ground. Somewhere beneath your feet, locked in ancient zircon crystals, is evidence of an ocean that existed before most scientists thought oceans were possible. You're standing on a palimpsest. Every layer is a different Earth. And all of them, somehow, led here. That's the thing no textbook ever told me when I was first learning about this. They teach you the Cretaceous, they teach you the dinosaurs, they teach you the Ice Age, and somehow they skip the part where the planet beneath all of that had already been through several complete cycles of near destruction and total reinvention before any of those famous chapters even began. I remember the first time I read about the Hadean Eon properly, not the sanitized paragraph version, but the actual research, and thinking, why didn't anyone lead with this? This is the most extraordinary origin story on any planet we've ever studied, and we buried it in the back chapters. So here's what I want to leave you with, now that we've walked the full length of it together. The hook at the beginning of this journey asked a question that sounds like a contradiction: how can there be an Earth before Earth? And we've now seen exactly how. Not as a metaphor. Not as a philosophical puzzle. As documented, peer-reviewed, crystal and rock anisotope verified geological fact. The Hadean Earth was a different world. Its atmosphere was the wrong color. Its oceans were the wrong temperature. Its continents, the few that existed, were arranged in configurations that would be unrecognizable on any map. And yet the chemistry was already working. The zircons were already forming in liquid water. The first self-replicating molecules were already beginning the long, improbable process of becoming something we'd eventually call life. 4.5 billion years is a number that resists comprehension in the same way that the distance to the Andromeda Galaxy resists comprehension. You can say the words, you can write the digits, but some part of your brain refuses to actually process what it means. So let me try one more compression, one last attempt to make that number feel real. If you compressed the entire history of Earth into a single calendar year, January 1st to December 31st, humans in our current anatomical form appear somewhere around 1158 on the night of December 31st. The entire span of recorded human history, every civilization, every war, every scientific revolution, everything we've ever built or destroyed, that fits inside the final 30 seconds of December 31st. The Cambrian explosion, with all its staggering biological innovation, happened in mid-November. The Great Dying, the worst mass extinction in Earth's history, happened in mid-December. Snowball Earth happened in October. The Great Oxidation event happened in late July. The first life, the first actual evidence of biology on this planet, appeared somewhere around late February. And the Hadean? The hellscape, the magma oceans, the meteor bombardment, the zircons forming in what should have been impossible water. That's January. The entire first month of the year. A world so alien and so violent that almost nothing of it survived except a handful of crystals small enough to hold between your fingers, and somehow, in those crystals, the first whisper of the ocean that would eventually, 4.5 billion years later, become the one covering 70% of the surface you live on. That's the real story. Not the dinosaurs, though the dinosaurs are extraordinary. Not the ice ages, though the ice ages reshaped everything. The real story is that this planet has been continuously, relentlessly inventing and reinventing itself since the moment it formed, using every catastrophe as a toolkit, never once running out of new configurations to try. There's a concept in geology called deep time, and it was first articulated clearly by a Scottish geologist named James Hutton in the late 18th century. Standing at the exposed rock face at Siccar Point in Scotland, layers of sediment folded, tilted, eroded, and then covered by fresh layers deposited horizontally on top, Hutton had what his companion John Playfair later described as a kind of vertigo. Looking at those folded layers, Hutton understood that the time required to produce them was incomprehensibly vast. He wrote, famously, that he could find no vestige of a beginning, no prospect of an end. He was looking at deep time for the first time, and it unmade his sense of scale entirely. I think about Hutton every time I read about the Hadean. Because what we now know about Earth's earliest history goes so far beyond what Hutton saw at Siccar Point that even his vertigo seems inadequate. He was looking at hundreds of millions of years compressed into tilted rock. We are now reading billions of years from crystals that formed before plate tectonics as we know it had even begun. The tools have changed: isotope mass spectrometry, molecular phylogenetics, high-resolution climate modeling, but the vertigo is the same. It's a feature, not a bug. It means you're engaging with the actual scale of the thing. I mentioned at the start that I wanted to find something definitive in all of this. A clean takeaway. And I want to be honest that I didn't entirely find one, but I found something better. What the geological record actually gives you, if you read it carefully, is a deep confidence in the resilience of process. Not the resilience of any particular organism, any particular species, any particular configuration of life. Process. The process of life seeking energy gradients, finding ways to metabolize, adapting to changing chemistry, diversifying into every available niche. That process has never, in 3.5 billion years of documented history, been permanently stopped. It has been set back catastrophically. It has been redirected. It has been stripped down to microbial survivors hiding in hydrothermal vents while the surface burned or froze. But it has never stopped. That's not a promise about any particular outcome. It's an observation about tendency. And I think it's worth sitting with. The question this leaves open, the one I genuinely don't have an answer to, and I suspect no one does yet, is whether intelligence changes the equation. Whether a species capable of reading the geological record, understanding the mechanisms behind past extinctions, and in principle deliberately modifying its own impact on atmospheric chemistry represents something genuinely new in Earth's story, or just a faster and more dramatic version of what cyanobacteria did 2.4 billion years ago. Cyanobacteria didn't know they were reshaping the atmosphere. They were just metabolizing. The oxygen was a byproduct. We are, at minimum, in a position to know what we're doing, which is either the thing that makes this version of the story different from all previous versions, or it's simply a different kind of catastrophe with a slightly more self-aware protagonist. I don't say that to be bleak. I say it because I think the distinction matters enormously, and the geological record is very clear that the outcome of the cyanobacterial oxygen event was ultimately, after hundreds of millions of years of consequences, the precondition for all complex animal life. The catastrophe made us possible. Whether our current geological signature will ultimately do something analogous, or whether it will simply join the list of extinction-triggering events in the stratigraphic record, is the open question that this entire 57 minutes has been building toward. And that question, unlike most of the questions in this video, doesn't have an answer yet. It's being written right now by the chemistry currently accumulating in the atmosphere, by the decisions being made in the decades we're currently living through, by whether the species that first developed the capacity to read its own planet's history also develops the capacity to use that reading as an actual guide. The geological record doesn't offer comfort. It offers perspective. It says, this is a long story, catastrophe is not the end of it, and the most significant turning points rarely look like turning points from inside them. The organisms that survived the Great Dying didn't know they were the survivors of the worst extinction in 500 million years. They were just the ones that made it. What they made it into, the world of dinosaurs, the world of mammals, eventually the world of us, was invisible to them. We are in the unusual position of being able to see that pattern. The question is what we do with the seeing. If you've stayed with us for this entire journey, from Hadean fire through snowball glaciation through the Cambrian's biological riot through 5 mass extinctions and out the other side into the present and the deep future, then I want to tell you something directly. Most people will never think seriously about any of this. Not because they lack the capacity, but because daily life doesn't demand it. The geological timescale is not urgent in the way that the news cycle is urgent. The deep past doesn't feel as immediately pressing as next year. But I think something shifts in how you see the world when you actually reckon with Earth's full history. When you understand that the oxygen in every breath you take is the waste product of a bacterial revolution that nearly froze the entire planet. When you know that the carbon in your body was forged in stars that exploded billions of years before this solar system formed, then cycled through the Hadean crust, then through the first oceans, then through billions of generations of organisms, before ending up temporarily arranged into you. When you stand on any piece of ground anywhere on this planet and know that beneath you, in the rock, is a stratigraphic record that goes back further than most people will ever think about. That knowledge doesn't make daily problems smaller. But it does change the backdrop. It gives you what Hutton had at Sitkar Point, a sense of the actual scale of the story you're embedded in. And scale, it turns out, is clarifying. The Earth has been through worse than anything currently on the table. It has rebuilt from conditions that make the worst-case scenarios of our current moment look manageable by comparison. Life has threaded itself through every needle the solar system has thrown at this planet for 3.5 billion years, and the current version of that thread includes the first organism ever to understand the history of the needle. That is not nothing. That is, depending on how you look at it, either the most dangerous development in Earth's biological history, or its most interesting one. Possibly both. And if wondering which one it turns out to be is enough to make you want to keep watching this corner of the universe with us, then we'll see you on the next one, because the Milky Way apparently contains somewhere between 100 billion and 400 billion star systems, and at least some of them are running their own version of this exact experiment right now, 4.5 billion years into their own particular clock, and James Webb is just beginning to read what their atmospheres are made of. Which means the most unsettling and the most exhilarating realization you can take from everything we've covered tonight is this: we are not the audience for Earth's story. We are, for the first time in 4.5 billion years of that story, a character who knows they're in it. And the next chapter is the only one that has never been written yet, which is either terrifying or the most extraordinary invitation ever extended to a collection of temporarily organized stardust, and honestly, from where I'm standing, it's both at exactly the same time. So if you're the kind of person who finds it impossible to sit with that and not immediately want to know what those atmospheres are actually made of, what James Webb is already finding around other stars, around other worlds running their own 4 billion-year experiments in chemistry and time, then the next video is already waiting for you, because we went there, and what the telescope found reshaping everything we thought we knew about where life can exist in this universe is, without any exaggeration, the most groundbreaking shift in planetary science since we first pointed a camera at a pale blue dot and realized just how alone it looked against the dark. And that pale blue dot, 4.5 billion years old, scarred by impacts and glaciations and mass extinctions and the slow patient chemistry of organisms that never knew they were building a world, is still, as far as every instrument we have can determine, the only place in the observable universe where any of this happened consciously. Where the universe looked back at its own 4 billion-year experiment and thought, wait, how did we get here? That question, asked by a species made of the same carbon that has been cycling through this planet's crust and oceans and atmosphere since before there was oxygen to breathe, is either the most improbable accident in the history of matter, or it is exactly what matter does when you give it enough time and enough heat and enough catastrophe to work with. The geological record does not resolve that question. But it does make it impossible to ask it casually, once you've actually seen the depth of the archive underneath your feet. So go outside tonight, if you can. Find a piece of rock, any rock, a driveway stone, a cliff face, a riverbed pebble, and hold the knowledge that what you're touching is a page in the longest book ever written, in a language of pressure and heat and time that took us until the late 18th century to even recognize as a language. James Hutton stood at Sychar Point in 1788 and saw deep time for the first time, and reportedly said that he found no vestige of a beginning and no prospect of an end. He was looking at folded sandstone. The same sandstone that contains, if you look at the right layers, the chemical signatures of every atmosphere this planet has ever run, every ocean chemistry it has ever tried, every mass extinction it has ever survived. All of it, still there. Still readable. Still telling the story of a planet that has never, in 4.5 billion years, once stopped trying. Neither, as it happens, have we. And if you want to know what those rocks are saying about the worlds currently forming around other stars, if you want to stand at the equivalent of Sychar Point for the entire galaxy and hear what 4.5 billion years of chemistry sounds like when you scale it up by 100 billion, then stay right here, because that is exactly where we are going next, and the universe, it turns out, has been keeping records far longer than we have. The rock in your hand was here before the first animal ever grew eyes to see it, before the first fish ever crossed from salt water into fresh, before the first root ever split stone looking for purchase in a world that had never known a root before. It was here when the oxygen first reached concentrations high enough to be toxic, when the snowball closed over the equator, when the Cambrian sea floor erupted into the most astonishing biological experiment this planet has ever run in a single geological moment. It was here through all 5 of the great extinctions, through every reset, every rebuilding, every improbable threading of the needle that eventually produced the atmosphere you are breathing right now, the precise chemical window that makes conscious thought possible on the surface of a rocky world at this particular distance from a medium-sized star. Hold that. Not metaphorically. Actually hold the weight of it, because that is the archive. Not in a museum. Not behind glass. Right there in your hand, 4 billion years of iteration compressed into something you could skip across a pond. The version of Earth that existed before the one you learned about in school was not a failure. It was a draft. The Hadean crust, the zircon oceans, the iron-breeding bacteria, the methane sky, the purple mat spreading across shallow shells of a world that had no name and no witness, none of that was prologue. It was the experiment itself, running in full, reshaping the course of everything that followed. Every mass extinction was a chapter break, not an ending. Every snowball thaw was a rewrite that kept the best parts. And the Cambrian explosion, that 30 million year sprint through every body plan life has ever tried, was not a beginning either. It was what happens after 3 billion years of invisible chemistry finally finds a door and walks through it. We are what walked through the most recent door. And the geological record, patient, unexaggerating, written in the language of pressure and heat and time, is very clear on one point: there will be another door, and something will walk through that one too, and it will look back at this moment the way we look back at the Ediacaran, with the particular mix of wonder and vertigo that comes from understanding just how long the story was running before this chapter started. The most groundbreaking thing the rocks have ever told us is not that we are small. It is that small things, given enough time and enough catastrophe to work with, eventually look up. And we, 4.5 billion years into this planet's particular experiment in chemistry and survival, are the first arrangement of that planet's matter to know the full length of the story it is embedded in. That is not an accident to be taken casually. That is, by any measure the geological timescale can offer, the most extraordinary development this pale blue archive has ever recorded. Go find out what comes next.